Hello, welcome back. So today we are going to be talking about physical design and timing using the Jurassic DE1-SoC board. In today's video, we'll be understanding the physical design of the FPGA tool flow, learn how to control the placement through chip planner, and understand the impact of placement on timing of the circuit. Also, at the end of this video, we'll be going through programming of FPGA using a batch script instead of the Quartus Prime application. To understand the physical design and timing of the Jurassic board, I've used the IR sensor module, which will transmit data using the IR transmitter and receive the data using the IR receiver. So in this experiment, only thing we'll be concerned is the STC constraints and chip planning. So everything else remains the same. To get a benchmark, first we will set the clocks to 20 nanoseconds. I've used 4 clocks here, all set to 20 nanoseconds. If we go to the timing analyzer and verify the Fmax and timing, that will provide us the benchmark based on which we'll be modifying the constraints and chip to see how the physical design affects the timing. Here, the benchmark is 182 megahertz. So this is the max frequency this design will run given the constraint of 20 nanosecond clock period. Let's get the detailed report of the critical paths. I've mentioned as I mentioned the report to provide me 5 paths. This will analyze the critical paths and provide us the information. As you can see, the report provided us 5 paths with all having 14.516 nanoseconds as the slack and 5.229 as the delay. If we select any one of the path or the path with the smallest slack, that will be the longest path, and go to chip planner. Once the chip planner opens up, we can see that based on our design and design constraints, the place and route protocol has placed the registers and all the resources in one place, and this highlighted arrow marks are the critical path. We'll use this as a benchmark to see how variation in clock period or variation in physical design affects the timing of the overall design. So let's go and change this to 2 nanoseconds and compile the design. Now the design has been completed. Let's go to timing analyzer to see how varying the clock constraints to 2 nanoseconds has modified the timing of the design. Our Fmax has increased to 230 megahertz, and let's check the critical path, report timings, and report 5 paths. So as you can see, we are getting negative slack. That means our design needs more time than the provided clock period. So that is the reason we are getting a violation here. That means we are trying to design the system where the critical path takes more time than the provided constraints. Now let's set the clock to 20 nanoseconds, but instead of providing changes in the clock period, we'll perform changes on the physical design. How changing the physical design will vary the final timing of the design. So now the design has been completed. Let's go to timing analyzer. Since we set it back to 20 nanoseconds, we can see that the Fmax has returned to 182 megahertz. Let's go to report timings and report the 5 critical paths. We'll get the same result since our clock has been set back to 20 nanoseconds. Let's select the path with the smallest slack. Locate path, locate in chip planner. This will bring up the chip planner. In order to edit the resource placement on the chip planner, we'll change the editing mode from echo to assignment and select the zoom tool, and let's zoom into our resources. So as you can see here, this is the critical path of our design. In order to do any modifications, first let's select our resource and move it to the point where we want to place it. So once the placement has been done, we'll have to just close it. Once the resource have been moved on the chip planner, we'll come back to the compilation tool and compile the whole design with our modifications. Okay. Once the compilation has been done, we'll go to timing analyzer and see whether the changes are being implemented. Report Fmax As you can see here, the Fmax has dropped to 88 megahertz. Let's go to report timing to see the 5 critical paths. As you can see here, from 14 nanoseconds, our slack has dropped down to 8.6 nanoseconds. Let's select the smallest slack, locate path, locate in chip planner. Comparing this resource placement to the previous, where everything was clustered to the right side of the chip, but later we moved the resources to left corner and bottom left corner and top left corner. All of them have been clustered more towards the left to avoid the delay as much as possible. So here is the base of the resources, which then goes to the top module and then comes down all the way to the bottom of the chip and then again routes back to middle of the chip. So this is the modification that we have done on the physical design, and the results can be seen on the timing analyzer, where the slack has reduced close to half and even our Fmax has dropped by 50%. So yeah, so those are the main things that we can see by modifying the clock period or by modifying the placement of the resources on the chip. So now let us have a look at how we can program the board without using the application. So for that, we'll have to run a batch file, which in turn calls up the subroutines of the application that is responsible for dumping the SOF file onto the board. So this program basically looks for where the subroutines are placed, calls those, and provides the necessary information, whether it is the board information, the SOF file, and all these required information so that the subroutines can program the device instead of using the GUI application. So to do that, we'll have to provide we'll have two files. One is the batch file itself and the SOF file. The SOF file will be generated once the compilation has been completed. So let's go ahead and program the device. We'll just select the batch file and hit enter. After doing all the preliminary checks, we'll start programming the device. And once that is done, we can see that by pressing the switch, the transmitter will transmit the data, and that same data is being read by the receiver. Here it is just sending a random data to so as you can see here, this is the transmitter and this is the receiver. So once we press this button, the transmitter will transmit random data which will be read by this receiver. Since it is an infrared connection, it is not visible to the naked eye, but you can see on this camera there is a purple light that is visible on the transmitter. So yeah, so that's the experiment of running a IR transmitter receiver on the Jurassic board, where the main aim of this experiment was to learn about physical design and timing. We learned how modifying the timing of the design will in turn make changes to the critical path, whether it will have a positive slack or negative slack, and how modifications to physical design will have a effect on the timing of the whole design. We saw that when we place the chips in the worst case, that is placing the chips completely to the bottom of the chip and completely to the top of the chip, how it reduced the overall slack or the overall Fmax by 50%. And then we use the batch file to program the device instead of using the Quartus Prime instead of using the Quartus Prime application. So yeah, thank you. Have a great day.